Kia ora koutou, nau mai, haere mai. Welcome to lesson 30 for introductory physics. This is the third and final lesson for the electromagnetism section, where we've been looking at electric forces and circuits, and now we're going to bring magnets into the mix as well, the other half of electromagnetism. Then there will be 6 more lessons after this one to cover waves, optics, light, and that whole section there. As you may have noticed, when we talked about light in previous lessons, we talked about it as electromagnetic radiation. Electromagnetic, meaning relating to electromagnetism, which is what we're looking at in this lesson. So in order to fully grasp what we're talking about when we do get to light, in the second half of the next section, please do take the time to understand this lesson in full. Our goals for this lesson are to be able to sketch and interpret electric fields, define electric field strength, sketch and interpret magnetic fields, define magnetic field strength, so that's the same things for both electric and magnetic fields. Then we want to talk about the interactions between them, so defining the magnetic field created by a current, explaining the term electromagnet, and describing the effect of a magnetic field on an electric current. So just a quick look at some of the interactions between electric fields and magnetic fields. So the first part of that is electric fields. So this is talking about the idea of electric charges that we've already looked at, but a way to visually describe the effect of a charged particle on the environment around it. Suppose we have some specific charge, Q, and we want to get an idea of how this charge might affect other charges in general, not at one specific location. We're not saying here's one particle, here's another, what's the force between them? We're saying here's one particle, what would be the force on any particle anywhere around it, right? What would be that force? So of course we could start by taking a few example positions. Let's go and choose a spot and calculate what the force would be for some particle. We need to choose what the charge would be on that particle, so we can choose something simple like a single proton. And that's what we do. We look at a whole bunch of different locations and we say, all right, if we had a single proton at this location, what would the force on that proton due to this single charge that we're looking at, what would the force on that proton be? And we figure that out. And of course, we already know what that's going to look like because we've covered Coulomb's law. So we know that if we go and put a proton at some position, then if we've got a positive charge Q, we will get a repulsive force because they're both positive. And the closer we get that proton to our charge, the stronger that force will be. We already know that, and we can calculate the exact magnitude of that force if we know Q, since we know the charge on a single proton. But of course, it's not just a straight line. We could choose anywhere in the universe really, but anywhere in the location of this charged particle. And we might not bother drawing our little test proton every time. That's going to get pretty tiresome if we had to draw a little circle with a plus in it every time we wanted to draw one of these vectors. So what we do is we just draw the vector. We don't worry about drawing the little proton every time we calculate the force at a specific location. And so our diagram might look something like this. We will tend to limit ourselves to 2-dimensional electric fields just because drawing in 3 dimensions is difficult. If you're using computer software, it's much easier to generate a 3-dimensional picture of an electric field, and you can navigate through that in the 3-dimensional space of the machine. But when we're drawing by hand, or if we're creating a diagram to print out or look at in a lecture slide like this, we stick to 2 dimensions just because it is easier. But remember that it is happening in 3 dimensions. You could put the particle above the Q charge if you wanted. It doesn't have to be in the same plane as that charge. And so this gives us hopefully what we would expect. The closer you are, the bigger the force, and it always points directly away from the charged particle Q. If you're right next to the charged particle Q, you get a big force away from it. The further away you get, the smaller that force gets. So we've got all these different force vectors. Now remember that these are just example vectors. There is of course a force anywhere you put the particle. You don't have to put it exactly at one of those spots. You could go and put it anywhere in the universe, as I said, and it would experience a force due to this charged particle with Q charge on it. But because we can't draw infinite numbers of vectors in our little diagram, we just choose a sample of them and we try and keep it symmetrical and keep it clean. And so we get something that looks sort of like that diagram there. Now that's great, but it's also not yet fully flexible diagram, because as I said, it's just showing you the force vectors at those specific locations. So what we can do instead is we basically connect all of those up. We take all of those force vectors and we just draw lines connecting them all. So if I go back a slide again, if you take one of these vectors and look at the point of the vector, the end of it, where the arrow tip is, the next one starts just past that, and it keeps going in that same direction. The next one starts just past that, and so on. And so if you do that, if you figure out the force vector, and then wherever that force vector ends, you figure out a new force vector, and then where that one ends, you figure out a new one, and so on. In this case, they're just straight lines, so it's very easy, but even if they're not, you can just follow that process. What you get is a line when you join them all up. And in this case, the line will be directly away from the charged particle, but it won't always be, as we'll see. And that line represents the direction of the force. So we've lost the magnitude of the force. What we've done now is we're just drawing lines showing the direction of the force. So that's basically the path that a charged particle, a test particle, would take, a proton. Remember, it's always a positive test particle, a single proton. We put that single proton somewhere and it will just follow one of those paths. Again, we've only drawn 8 of them here. There are infinite of them, because no matter where you put that proton, it will follow a straight line path away from that positive sign, from that positively charged particle in the center. But because we know that we can see these 8 test lines, these example lines that point away, we know that if we go and put one in between, it would just follow that same pattern, because this is a very patterned diagram. We've got these nice radial straight lines pointing directly away. We can look at that and we can figure out that if you put it anywhere in between, it would still just follow a straight path, but it would be along the path that you put the proton on rather than one of these ones. These lines are called field lines. Sorry, I didn't pronounce the D very clearly there. They are called field lines. Field lines, just the way we represent the direction of the Coulomb's force on a charged particle due to some main charged particle, so on a test particle due to this charged one. So this is our actual charged particle Q that we've been talking about the whole time in the center here, and the lines represent what a proton would do if we took a single proton and put it down in that region of that charged particle. I said when we turned all those force vectors into lines, we lost the magnitude, we lost the strength of the force, and we're only left with the direction. And that is sort of true, but the magnitude is actually hidden in this diagram in terms of how close the field lines are together. Remember that the stronger the force was, if I go back a slide, the stronger the force was, the closer to the particle it was, the closer those lines look. When you get further away, because we're still only continuing each line, we're not adding new lines in, as you get further away, the lines are now further apart, and that's where those field lines, those force vectors were shorter. They had a weaker force. And so we use that idea. So we connect the vectors up to create the field lines, and the closer the field lines are together, the stronger the force is going to be on our test particle if we put it there. So if you take a proton and you put it down close to this charged particle, you can see that the field lines are all closer together than if you put it a bit further away. And so we use that idea of the strength as being represented by the closeness of these field lines. And that's all an electric field is. Right? An electric field is a way to visually describe the effect of a charged particle on other charged particles in its region. And we do that by drawing these field lines. I do expect you to be able to sketch a field diagram for a simple single charged particle. I don't expect you to draw them for multiple particles. As we'll see, they get a bit more messy, but you should still be able to interpret them. The general rules for drawing electric fields or interpreting them are that the closer the field lines are together, the stronger the electric field is. I just said that one, right? The stronger the field, the closer the lines are going to be. Field lines always have arrows. Remember that they are directions, they are paths that a positive charge would take. So you have to include that direction. But do remember that it's the direction a positive charge, a single proton, would travel. That means if you took a single electron and put it on one of those pathways, it's going to travel the opposite direction, just like we talked about with conventional current. So you have to think about what the particle is versus which way that field line is pointing. And the other thing is that field lines will always start on positive particles and end on negative particles, because if you've got a positive test charge and you put it right next to a positive charge, then it will be repelled. So they will always start there. They'll always be heading away from a positive charge. And if you put it near a negative charge, it will be attracted to it, so it will just stay there. It's the end of the path. It can't really go anywhere because it's now met that negative particle, and it will stay put. So they always start on positive particles and end on negative particles. As I said, if we have an electric field, the field tells us what a proton, a positive test particle, would do. But we want to know what would happen to any particle, not just a positive one and not just a proton. We want to know what any charged particle would do. So what we do is since we calculated the force when we were creating our electric field, I didn't show you any of that, we just drew the force vectors on, but in order to draw the force vector, we had to calculate that force. Because we calculated that force, we know the force on our test proton particle. And just like we saw with electric potential energy versus electric potential, we had this idea of dividing by the unit charge, right? Dividing by the amount of charge so that we get this generic term that can apply to any particle. And we do the same thing here. We take this electric field strength, right, the electric force from our test particle, and we divide it by the charge on that test particle. So in the case of a single proton, you divide it by that charge on a single proton, and that tells you the force per unit charge. And that way, no matter what particle you put there, you are going to be able to tell what the force on it would be by using this electric field strength. So that's all it is. You figure out the force on a test particle and you divide by the charge of that test particle. Of course, if you're using Coulomb's law to figure out the charge on the test particle, then you don't really need to calculate the force, because F is equal to K Q1 Q2 over R squared. You can just cancel out that Q, the test particle Q, right away, and you're left with K times the charged particle that you're concerned with, that you're drawing the electric field for, divided by that distance squared. Electric field strength, hopefully you can see that's going to have units of newtons per coulomb, but it also has units of volts per meter, right? Volts per meter as well as newtons per coulomb, and that's a good exercise to go in and check that those units actually work, that they make sense. Once you know the electric field strength at any location, which we use the letter E to represent, as you saw on the previous slide, so the electric field strength E at any location, then the force on any charged particle that you place at any location, or at a specific location rather, we're talking about a specific location, the force on that particle will be that electric field strength E times Q, the charge on the particle that you just put there. So that is essentially calculating Coulomb's law. It's just using this electric field strength as an intermediate step so that we don't have to do the full Coulomb's law calculation every time. As we already saw, with a single charged particle, the electric field is very simple. It's just radial fields, right? Radial meaning straight out from the center, right? Radial like the radius of a circle, just straight out from the center outwards. That's all an electric field will be for a single point charge. A negative point charge will look exactly the same, but the arrows will be pointing inwards, because remember, field lines leave a positive particle and go into a negative particle. So a negative one would look exactly the same, but pointing inwards. As I mentioned, when we have multiple charges, you get complex curved electric fields. You do not need to know how to draw or calculate these, but there is no reason you can't understand them. And I believe on the worksheet I have included, I've just drawn an electric field that you can have a look at and try and interpret. The other thing that I may not have mentioned specifically, but I did hint at it, the stronger the electric field, the closer together those electric field lines will be. And that means that if you have two charged particles of the same magnitude, they must have the same number of electric field lines going in or out of them. And so you can see here that in the center diagram here, this positive particle, we have, what is that, like 10 roughly, no, 12 field lines coming out of each positive charged particle. We don't know what strength those field lines represent, and so we don't know what the charge is on that positive particle, but we know that because those two fields, the two sets of lines coming off the positive particles both have 12 lines, that those two particles must be the exact same charge, right? They must have the exact same charge on them because they're both creating the same number of field lines. If one of them had more charge, then the force on a test particle close to it would be stronger, the lines would need to be closer together, and we would need more lines there. Right, so the fact that the lines, there's the same number of lines coming off each one means the separation between all the particles, all the field lines, sorry, is the same. So the two particles must have the exact same charge. Whereas on the right-hand diagram, where we've got a positive and a negative, you can see that there are a lot more lines coming off the positive than there are going into the negative. Right? You can tell that because a bunch of the ones coming off the positive are going into the negative, as well as one more that's coming in from directly opposite the positive. But we've got a bunch of field lines going into the negative from the positive, but we've still got heaps more coming off the positive that are going off elsewhere into space and not ending up at this negative particle. So even though we haven't counted the lines, you can if you want to, but even if you don't, you can tell that the positive charge is giving off more field lines than the negative charge is receiving. So the positive charge must be greater in magnitude than the negative charge is. So using things like that, looking at these diagrams and sort of interpreting these field lines, there's nothing to stop you being able to do that. Although, as I said, I do not expect you to be able to create these diagrams. They do get complicated. The maths is quite difficult, but certainly being able to sketch fields for simple single particles is easy. They're all just radial lines. And for multiple particles, don't need to be able to sketch them, but you do need to be able to interpret them. Sometimes we want a uniform electric field, uniform. So a uniform field is one that will result in the same force, both magnitude and direction, no matter where your test particle is. So it doesn't matter if you go here or here or here or here, the field, whatever the field is, it should always produce that exact same force. So always in one specific direction, always the same magnitude, no matter where you go within it. That's what uniform means. That's the same sort of idea as uniform in everyday language, just always the same. That means that our field lines must be evenly spaced. Remember, the distance between our field lines is the strength. So the field lines have to be evenly spaced, and they have to always be pointing in the same direction. So they have to always be parallel. So how do we create that? When we saw that a single charged particle creates field lines that point out radially, and multiple charged particles get all these curved surfaces, curved lines, how do we create an electric field with nice straight parallel lines? It actually turns out to be pretty straightforward. All we need to do is use large flat objects, right? Large flat objects, charge them up, and then the electric field between them will be nice parallel straight lines, as per the diagram here. At the very edges, it will start to curve because now we're not getting any charged particles out here. It means that you will get this curvature as you get out beyond it. But within most of the region of the center, so just stopping a bit short of the edge, most of this area in between the two charged objects will be a uniform electric field. That is something that we actually use a lot in physics when we're doing experiments and we want to test particles and observe them. And so we want to create uniform electric fields. And we've actually got an experiment in our third year physics lab where we test we determine the charge on a little droplet of oil, tiny little droplets that effectively are light enough that they'll float in the air and they'll just sort of bounce around a bit in the air. And we can use an electric field like this, a nice uniform electric field, and we can turn on the charge. We have a little voltage dial, and we can turn on the charge on the long flat plates, change that electric field strength, and watch what happens to that little oil droplet. And that oil droplet has a charge on it, and if you turn on the plate and you watch the droplet accelerate upwards or downwards, you can figure out the exact amount of charge on that droplet. And because that droplet has been ionized, it's always going to be a number of whole electrons greater or less than it would need to be neutral. You don't need to remember any of this. The point is, what I'm describing is the Millikan oil drop experiment. And it's a famous experiment in which Millikan found the charge on a single electron. So we know the charge on a single electron is 1.602 times 10 to the minus 19 coulombs. He's the guy that figured that out, right? And he used the Millikan oil drop. And to do that, he needed this idea of a uniform electric field. As I said, when we draw electric fields, we often just stick to 2 dimensions because getting into 3 dimensions is very difficult. But sometimes when we're drawing a field, we want to represent a field going perpendicular to the page. So we might be drawing the path of a charged particle, but that particle might be going through a field which is actually coming out of the page or into the page. And so we want a way to be able to draw that, to represent that on our diagram. Excuse me. Represent that on our diagram. And the way we do that is with these symbols right here. And that is a circle with a dot through it means coming out of the page towards you, and a circle with a cross through it. And this doesn't mean a light bulb in a circuit, but a circle with a cross through it in this case means an electric field going into the page. Some people do have problems remembering that. That's understandable. These arbitrary symbols I suddenly give you and expect you to remember. So I'll just show you the little trick for remembering those if you are struggling, and that is to think of an old-fashioned arrow like from a bow and arrow. So an old-fashioned arrow like this, and on the end we have these feathers. Forget what they're called. People have told me in the past, but I always forget. So we've got an old-fashioned arrow like that. If you look at this arrow from the front, so if you were to go and look at it from here, that is going to look like a circle with a point. So it will look like that. Right? And so that's this arrow coming directly towards you. And that's what we use as the symbol for an electric field coming directly towards you. If you were to look at this from the back, then what you're going to see is you're going to see this circle from behind, but you're going to see the crosses of these feathers, these fletchers, I think there's something like that, from the back of the arrow, and that's going to look like that, roughly. So obviously not a perfect example, but it does hopefully help you remember which is which, right? The circle with the point means it's coming towards you. It's the tip of the arrow. The circle with the cross, you're looking at the arrow from behind. It must be going away from you. I still use that, right? It's not, obviously doesn't take me long, and I still look at it and I go, yeah, that's coming towards me, but I'm still subconsciously just going, that's a tip, that's the point coming towards me, right? So that is a useful way to remember which way these field lines are going. We've talked about conductors. Conductors are the things full of electrons, and the electrons are free to move around, and electrons can carry electric current and so on, and they can have a positive charge or a negative charge. But what is the electric field inside a conductor doing? Remember that the conducting electrons inside the conductor, the electrons can move, that's why it's a conductor. Those electrons, if you have too many of them or too few of them, will distribute themselves on the surface. So extra electrons will be on the surface, the missing ones would be on the surface. Right? The surface is where they would be if they were there. So you're always getting your charge on the surface. And that means that the whole inside of the conductor is not charged. It's not charged. And that means that there isn't any force on a charged particle inside the conductor. So we don't have any electric field inside a conductor. And this is always, always, always true. There is no electric field inside the conductor. The field lines start or end on the surface of the conductor, but they never go through the conductor. Right? So they start or end at the charged particles, and those charged particles are on the surface of the conductor. Right? And so in terms of the scale we're talking about, we'd never draw electric fields inside a charged particle. Some of you might be thinking, well, there are protons and electrons inside the conductor, so there must be some electric field. Yes, technically there is. There are protons and electrons, but they're all little field lines going just from the protons to the electrons, and that's what's holding the atoms together. Remember, the protons are attracting the electrons, and so they orbit and so on. And so you do technically have little bits of field, but they're all what's holding the atoms together. We have none of this strong field that has an effect on other particles. That is only ever going to be happening outside of our conductor. As we said, they must go away from the positive particles or towards the negative ones, so it would look exactly the same. So you can draw a spherical charged conductor the same way you would draw a single charged particle, as we saw earlier. So that's the end of our section on electric fields. We're now going to introduce magnets and talk about magnetic fields. We all know what magnets are. We're used to them. They're common on fridges and in toys. So we've all played with magnets enough to have an idea of what will happen. And the main idea being that if you put them one way and push them together, they will repel. If you turn them both around, they'll still repel. But if you just turn one around, they will attract. So you've got this idea that one way they'll repel, one way they'll attract, right? And that's very similar to what we saw with charged particles, with electric fields and forces. In the case of magnets, though, we have magnetic poles rather than charges. So we're all familiar with compasses as well. If you hang a magnetic bar, any little magnetic bar, if you perfectly balance it and hang it right from the center, or put it on a pin so that it can rotate like in a compass, then that bar, that little magnet, will align itself with the magnetic field that it is in. We haven't defined magnetic fields yet, but it'll be in one and it will align it with itself with that field. That field is generally just Earth's magnetic field. If you're just out in the open in the countryside, the field that you are in is Earth's magnetic field, because Earth has its own magnetic field. The end of the compass, which points towards the geographic north pole of Earth, is the north pole of the magnet. That's the way we've defined it. The point of the compass that points north is the north pole of the magnet. And so that allows us to just go back to what we were saying about this repulsion and attraction, but define it in terms of these poles now. So we have a north pole and a south pole. And if you try and push two north poles together, they'll repel. Two south poles, they'll repel, but a north and a south will attract. Again, just like we saw with electric charges. Two positives repel, two negatives repel, but a positive and a negative will attract. Same deal. What happens if we break a magnet in half? This is a nice little conceptual question, because when we talked about charged particles, if you have a particle, an object, sorry, that has negative charges on one end and positive charges on the other end, and you break that, you're going to be left with a negative object and a positive object. They'll just be two separately charged objects. That's not the same for magnets. What happens with a magnet if you break it is that you get two smaller magnets. Magnets always have two sides. They always have a north end and a south end. So you can't get a magnetic monopole. It's not a physical thing. It does not exist anywhere in the universe. You can't just have a south magnet. A magnet is a thing which has a south and a north on it. It will always have a top and a bottom, a north and a south. If you want some repetition on that concept, as I tend to do, I'll just repeat myself basically, but with an extra little analogy here. If you have a block of wood, you've got a block of wood, then it's got, so this is a nice block of wood, It has a top and a bottom, right? It's just standing there on the bench. It's got a top and a bottom. Cool. You then go and cut that block of wood in half. Right? You cut it in half. What do you have now? Do you have a piece of wood that is just a top? Is this just a top piece of wood and this is just a bottom piece of wood? No, you don't. You have two new blocks of wood. Each one has its own bottom and top. So this part here is now the top of this block, and this part here is now the bottom of this block. So you have two new blocks of wood, both having a top and a bottom. And it's the exact same thing with magnets, right? With a magnet, magnets always have essentially a top and a bottom. So you can think about them as that, if that helps. But if you break a magnet in half, you are left with two smaller magnets, a north and a south on each. Magnetic field lines, just like we saw with an electric field line, is the direction that a magnet would align itself. So remember, you can't have a single pole like we saw with electric field. So there's a slight difference here. With an electric field, we said, let's take a test proton, put it somewhere, see what the force is on it. We can't do that. So instead, the test thing we do is a little compass. We use a tiny little compass and we put it down and we see which way it points, right? So that is, the north end of the compass will point towards a south pole or away from a north pole, and the south end of the compass will point towards a north pole or away from a south pole. So you can use the little compass and just map out the field lines that way. So it's very similar to what we did for the test proton particle in an electric field, but it's just slightly different because remember, we can't get a magnetic monopole. So we can't just take a north pole object and put it somewhere. We always have to have a whole magnet which has a north and a south pole. So we use tiny little compasses. If you continue that, you can draw out the whole magnetic field. And if you continue on to first year physics courses in Massey 104 and 105, we sometimes, I can't guarantee they'll still be there, but we sometimes do have lab experiments where you can you literally draw the magnetic field by tracing out where a compass points through the page. We have the same rules as we had for electric fields. The slight differences now because we've got north and south instead of positive and negative. So field lines always point out from the north pole, just like they always pointed away from electric positive, always out from north and into south. Remember, it's the way that a compass points. So the way that a north end on a compass would point, so it's always going to point away from another north. The difference here is with the way the loops, the magnetic field lines are created. In an electric field, they always started on a positive, ended on a negative. In a magnetic field, the field lines are always complete loops, but sometimes, or usually, the magnetic field loops go through the magnet itself. So you can see that in order for this to be a complete loop, it has to curve back around, go through the magnet, and then come out again at the north end. But they do that. That is what is happening. So electric field lines were never inside a conductor. Magnetic field lines are always inside a magnet. But again, the stronger they are, the closer together those field lines are going to be, exactly like we saw for the electric field. So it's pretty similar to electric fields, but with a slight difference. We mentioned that the Earth has a magnetic field. That's why compasses work. The Earth has its own magnetic field. It's like a big bar magnet. The one complication is that because we called the point of the compass that points towards the geographic North Pole, we called that the North Pole of our compass magnet. Remember that the North Pole actually points towards the South Pole. North is repelled from North magnetic, attracted to South magnetic. That means that our geographic North Pole must actually be a magnetic South Pole, and that is indeed the case. The geographic North Pole of Earth is the South magnetic pole of Earth. So the magnetic poles are actually the opposite to the geographic poles. And the other thing is that they're not quite perfectly aligned. The geographic pole, that's the one, the axis around which the Earth rotates. So remember, we talked about rotational motion. The Earth is rotating around itself. That axis, the line along which it's rotating, is the geographic pole. The magnetic pole is the point at which the north and south magnetic field lines sort of enter and exit the Earth. They actually do it everywhere, but the straight line through is at the north and south pole line. And that is about 11 degrees off from the geographic North Pole at the moment. So they're not quite perfectly aligned, but they're very close. And for the most part on Earth, it will point you in the right direction. But if you got very close to the North and South poles, so somewhere up in the Arctic or Antarctic, down in the Antarctic, then you would have to be aware of this distinction, this difference between geographic and magnetic south and north, so that you could find your way correctly. So magnetic fields are all curved. They're all curvy. They come out of the north end of the bar magnet. They curve around. They go back, curve into the south end, and they loop up through the magnet and just keep going because they're loops. So how do we get a uniform magnetic field? Right, just like we saw with a uniform electric field, we do the same thing. We get two big, long, flat magnets instead of two big, long, flat charged things. Now, these need to be one north pole or one south pole for this to work. As we said, you can't just have one, you can't just have a south pole. So these are actually both parts of big full magnets, but we're just looking close up at the end of them. It could in fact be one big curved magnet that goes around in a circle with a little gap in it. But regardless, you've got a north pole and a south pole, and you hold them really close. They'll be attracted to each other, but you hold them really, really close together, but strongly so they can't move towards each other. And again, just like we saw with the charged particles for a uniform magnetic field, this will create a nice uniform magnetic field with nice parallel straight lines pointing directly from the North Pole to the South Pole. And again, we'll get these little fringes, the curved bits at the edges as we start to get towards the edge of the magnet. But as long as we're working with that central region where the field is uniform, then we can do our experiments there and we know that the field is going to be uniform. As with electric field, we need to define our strength for magnetic fields. And in the case of magnetic field strength, that is measured in Teslas or capital T. Capital T is Teslas. 1 Tesla is defined as follows, as this statement. You do not need to remember this. You don't really need to understand it, but it should be pretty understandable once we finish this lesson. A particle of charge 1 Coulomb moving perpendicularly through a magnetic field of 1 Tesla at a speed of 1 meter per second experiences a force of 1 Newton. So it's that same idea that we had previously of using lots of ones to just make our our values, our units all balance out for simplicity. And so they've done it again, but so far you won't really understand that. The idea of a charged particle moving through a magnetic field experiencing a force, what's going on there? We'll look at that in a moment. But the point is that you can see 1 Tesla is equal to 1 Newton seconds per Coulomb. That is the units for magnetic fields. But all you need to remember is that we use capital T for Tesla. Here are some examples of magnetic field strengths. We have a human brain has magnetic fields of around about 0.1 to 1 picotesla. Remember pico, look that up if you've forgotten that prefix. From a toaster, about a 30 centimeter ruler away from a toaster, you're getting between 60 and 700 nanoteslas. 30 meters from a residential power line is between 100 and 500 nanotesla. The reason I include that is you may have heard, it's thankfully a fairly rare little conspiracy, but the idea that living near a residential power line will create magnetic fields that will interfere with you and cause mental problems and things. But as you can see, the magnetic field from a toaster is about the same as it is from 30 meters from a residential power line. And of course, their power lines are up high, so they're always quite far away. From a microwave, you get even stronger, 4 to 8 microtesla. Refrigerator magnets are all the way up at 5 milliteslas, usually around about that region. These are all approximate values. Loudspeakers, speakers work using magnets. They use the magnet to make the cone vibrate, which causes the sound. And those are up in the whole teslas and so on. So you can read through all of that. The one I do want to point out is 16 Tesla, a couple more down. 16 Tesla, field strength to levitate a frog. The field strength to levitate a frog, that is how strong the magnetic field had to be to make a frog float. So the idea that everything is made of atoms and atoms are full of electrons means that you can sort of get this response. So if you put something in a strong enough magnetic field, that the electrons will do that. We'll talk about this in a moment. Electrons can create magnetic fields, and they'll do that in response and push away. And at 16 Tesla, it was strong enough for all the electrons in the frog to push itself away from that magnet. And so it levitated the frog. The frog was completely unharmed. Magnetic fields don't damage living things. It's not a problem. So the frog just afterwards, it hopped away. It was perfectly fine. That was 16 Tesla. We can't create one strong enough to levitate humans because we are much heavier and the magnetic field will need to be a lot stronger, and we just can't do that. As we can see here, the strongest continuous lab-produced field, so the strongest field that anyone has been able to produce and maintain in a lab, is only 45 Tesla. That's only 3 times as much as the field strength to levitate a frog. So that there is our limit on what we could levitate using magnets. But if you produce a very quick magnetic pulse rather than continuing it, then we actually have the technology to get a lot stronger. But of course, you're not going to be able to do any levitation or anything because it's not continuous. It's just a little pulse. And that has been up to 1 kilotesla. That's the strongest pulse lab-produced field. Neutron stars. They're a type of star that's very dense and they've got a strongish magnetic field of 1 to 100 megatesla. I say strongish, that's very strong for all the other things we've just looked at, but there are specific types of neutron stars which have much higher magnetic fields and they can get up to 100 gigatesla. So there's a whole range of magnetic field strengths through the universe as one would expect. So now let's talk about that idea of electric fields and charged particles interacting. Let's have a look at that. And we can owe this entire field of study, electromagnetism, which is the joining of electric field or electric physics and magnetic physics, joining them together into one field called electromagnetism. And we owe that to Hans Christian Ørsted in 1820. When he was playing around and he noticed that his compass, when he moved it near a magnetic field, when he moved his magnetic compass near an electric wire, which was carrying a current, the compass was deflected, the needle moved, right? It aligned itself around this wire rather than with the Earth's magnetic field. So he realized that this wire carrying a current was creating its own magnetic field. If he turned the current off, then the needle wasn't deflected, so there was no magnetic field. But while there was a current, while that wire was carrying a current, so while the electrons were moving through the wire, he realized that that means there was this magnetic field being created. And so he realized there's this connection here, this thing that somehow, this property that somehow results in a magnetic force from a moving electric current. And so he played around and he found out that this is essentially that a moving current, or a current that is moving, a current causes a magnetic field that loops around the wire. Right? That's what happens. It's just a fact you need to learn, that if you have a current, a whole bunch of moving charged particles, it will form a magnetic field. We want to know which way the magnetic fields are pointing. We know that it's a circular. It's circular around the wire, right? And it's just concentric loops. That is what the field is. It means if you put a compass anywhere, it'll just point basically perpendicular to that wire, just in a circle around it. But we need to know which way. If you look down on top of this wire, is it going clockwise or anti-clockwise? Which way does it go? And he found out that if you use your right hand, then it's always the way your fingers would curl if your thumb points in the direction of the current. And this is the right hand rule version 1. So if you grab the current carrying wire, right, which you should only do if it's insulated, but if you put your hand around it, you put your hand around the current carrying wire, so here's the wire, you grab the wire with your thumb in the direction of the current. So if the wire is going upwards, my thumb goes that way. And so you grab the wire at the direction your fingers are pointing, that is the direction of the magnetic field. Right, so if the current was going down instead, you'd grab it that way, and your fingers are now pointing the other way. So the direction of the current will tell you the direction of that magnetic field. That means that if you take a loop, a wire loop, and you run a current through it, as I've drawn here in black, you've got this wire loop, you run a current through it, then everywhere you grab that loop, your fingers are always pointing the same way through the wire loop. Right? They're always pointing the same way. And that means that the magnetic field inside this loop is only going one direction, always one direction, and then outside the loop, it curves back around through space and comes back and comes through the loop again, because field lines are always loops. So it always goes through the loop, around it, and then back through it. What we have by running a current through a single loop looks very much like a bar magnet. And if you go and stack a whole bunch of loops together, make one big coil, like we've drawn on the left here, then the magnetic field going through all these loops is always pointing the same way. Because if you grab that wire anywhere with your thumb pointing in the direction of the current, your fingers are always going the same way up through that coil. And that looks exactly like what we saw with a bar magnet. And indeed, the coil, that loop of constant loops of wires on the left, is called an electromagnet. It is a magnet, but it's only a magnet when the current is switched on. And electromagnets are very useful for that reason. They can be created to be very strong. If you have a higher current, you get a bigger magnet. If you have more loops, you get a bigger magnet. But if you go and turn the power off, it's suddenly not a magnet anymore. And that's very useful for things like salvage yards and so on. If you go and want to pick up a big metal thing, you turn the electromagnet on, it attracts the metal, it picks it up just like a magnet does. But if that was a regular magnet, how would you get that metal off the magnet afterwards, right? It's very hard. You'd have to go and apply more force to the object to get it off than the magnet applied to it to attract it in the first place. So it gets very difficult to remove the objects. But if you've got an electromagnet, you can just turn it off and the metal will then fall off the magnet because it's not a magnet anymore. So electromagnets are very useful, and they are simply the result of coils of wire with a current running through it. Very easy. We have other uses for electromagnets as well. They are used in physics a lot. We use them for high energy particle physics because they can be used to accelerate particles. As I said, you can be used practically for moving scrap and other things. And then the other thing that they're very useful for is accelerating or decelerating trains, roller coasters, and other types of vehicles. Remember that magnets attract a lot of different types of metal, not all of them, but a lot of them. And if you turn on a magnet next to a piece of metal, it'll attract that metal and that'll force it to slow down, right? It's like friction, but it's not actually you doing any friction. There's no rubbing of metals, which means you're not going to have any wear and tear. So you can create these brakes, electromagnetic brakes, that won't actually get damaged and wear down over time. So as long as there's a current, then you'll get this this decelerating force. But you can do the opposite, and you can actually use it to repel metal and accelerate. It gets more complicated to do the acceleration in some senses. We're not going to look at details at that, but again, it's something that is very interesting. And if you're interested in that area, then looking up electromagnetic acceleration systems can be very interesting. Remember Newton's third law. If object A exerts a force on object B, then object B must exert a force of equal magnitude in opposite direction on object A. That means that if we saw a current carrying a wire apply a force to a magnet, right, because it changed the direction of the magnetic needle, the only way it can do that is if it's applying a force to that magnet. So if the current carrying wire is applying a force to the magnet must be exerting a force on the charged particles, on all those electrons that are causing the current. Because a compass needle is very small, it's a weak magnet, the forces involved are pretty small, enough to move that little magnetic, the magnet in the compass according to the magnetic field, but not enough to move the current carrying wire noticeably. But if we used a strong magnet, and put the wire inside the strong magnet, then turn the current on, then we might see the opposite. If the magnet's too big and heavy, the wire might move instead of the magnet. And indeed, that's exactly what happens. If you put a wire through a giant magnet and run a current through it, then you will get a force on it. You will get a force on the wire. The wire will be pushed down or pushed upwards. Which way is it going to be pushed? Well, we would have to figure out which way the magnetic field is and which way the repulsions are and stuff. And it's quicker just to remember the right-hand rule version 2. You probably realized the version 2 was coming when I called the first one version 1. In this case, we use another right-hand rule, and you put your thumb again in the direction of current, but this time you point your fingers straight in the direction of the external magnetic field. Right, so when they were curved, it was telling you the magnetic field that was resulting from the current. This time, instead, we use the fingers to represent the direction of the external magnetic field. And the way that you would push with your palm is the way that the force will be applied to the wire. So the example here with my very poor Photoshop attempt here is that if you point your thumb in the direction of the current, now sometimes it can be pretty difficult to get your hand into the right position, to sort of got to hold it like this to be able to see what's going on, right? It's kind of awkward, but you can hopefully visualize it. Just turn everything around if you need to, including yourself. Put your thumb in the direction of the current, put your fingers in the direction of the field, so from north to south, as per this photograph here. The way you would push with your palm is the way the wire will move. So the force here will be upwards, that wire will be pushed upwards. And so that's right-hand rule version 2. If you don't have a right hand, then you will need to learn the mirror image version with your left hand, right? And that is basically that you push with your back of your hand instead of your palm. But for right hand, push with your palm. This idea of a force on a current carrying wire is what drives electric motors. If you put a loop into a magnetic field, so you've got a loop of wire, then each side will have a force in the opposite direction, which will cause the loop to rotate. So here's your loop of wire. This side is being pushed that way towards the camera. This side is being pushed away. That means the whole loop is going to spin around, right? It's going to be rotated like that. Once they get to the full rotation point, right, so that this edge of the wire is now as close as it can get to the camera, and this one's as far away as it can, then what you do is you just swap the direction of the current. Right? You just swap the direction of the current, so now it's going the other way, and this part that was close to the camera is now being pushed away from the camera. This part that was far away is now being pulled towards it, and it just keeps spinning until they're back here, and then you swap the current again, and then it will rotate again, swap the current, rotate again, and so on. And you just keep doing that, and that is what an electric motor is doing. That's all an electric motor is. It's just this idea that a big strong magnet will apply a force to a current carrying wire. And that's the end of this lesson. So as I said, it was a fairly brief introduction to this idea of electromagnetism, to this interaction between electric charges and magnets and magnetic fields and electric fields and so on. But I do want you to understand what we were talking about with electric fields and magnetic fields, right? This interaction between electric charges and magnets is interesting and great and very, very common throughout society. We've used it for a lot of things. So do by all means understand that. But the idea of the fields, those electric and magnetic fields, you definitely need to grasp that in order to understand what we're talking about when we get to light and what light actually is.